Hello, I'm Matthew Krupcale. I'm working with Dr. John Lee on radionuclide atmospheric transport modeling, and I'm going to be talking about some of our Fukushima simulations as well as some of our volcanic ash simulations. So our goal here is kind of under the context of the CVT, the Comprehensive Test Ban Treaty, to be able to detect radionuclide signatures in particular from clandestine activities, including weapons tests. And we want to be able to localize the source, pick up the intensity of the explosion, and then we can make decisions based on that. And this is under the guise of the NNSA ground-based nuclear detonation detection roadmap. And so part of what we need to be able to do is assess some of the uncertainties in our source estimation, discriminate between civilian sources and clandestine ones. And some of the ways that we're going about doing that are benchmarking some of our atmospheric transport modeling codes, or ATM codes, with the available radionuclide data and other data sets, including volcanic ash data. And what we'd ultimately like to be able to do is coordinate our efforts with the seismic and infrasound data and incorporate different modes of data and come up with better decision-making capabilities. So our dispersion modelers are based on a advection diffusion equation kind of model of calculating the concentration in the atmosphere due to different sources, the source term being on the right there, and then we have diffusion coefficient, our Eulerian particle velocity, and our scavenging or wet deposition or radioactive decay terms. And so we solve this actually using a Lagrangian approach in which we transport particles and we use their localized frame of reference and integrate their trajectories using our meteorological data. And this is actually a stochastic Monte Carlo type simulation because while we have the average velocities from the wind fields of our meteorological data, we also have to incorporate the turbulence of the model, and that's done in a stochastic fashion. And for non-interacting particles, this is actually very convenient to use the Lagrangian approach because we can scale this very well, parallelized, and just integrate each particle's trajectory independently. But there are challenges with the meteorological data being such a large data set, on the average of 1 gigabyte per day of data for a global data set or more. And so that has I/O implications, and using large numbers of particles can make this very time-consuming computationally. So one of our first test cases is the Fukushima Daiichi nuclear accident test case, and we actually have IMS detector data from this incident, and we want to be able to estimate the radiological release from this event, and we parametrically studied the source time dependence and magnitude of our estimate based on the data. So the method that we're using, the code that we're using actually is called FlexPart. It's a Lagrangian dispersion modeler, and we used 1 hour global climate forecast data on a 0.5 degree global grid, and we assumed a time-dependent release spanning from March 12th through the 16th of 2011 in 24-hour periods. And the point source we released at the center of the units 1 through 4 geographically. And we used both noble gas and particulate species in our simulation with activity emissions estimated using actually an Origin 2 reactor inventory calculation. So the estimate of the source, as I said, is based on Origin 2, but we also have found references in the literature who have done source estimates, and so we've been able to kind of compare what the inventories were to the literature emissions, and then we came up with what our estimated release was based on the Origin 2 and literature values and fitting our data to the simulation model. So what we did was we assumed a 100% release of the noble gases, which is generally a fairly good assumption, but for the particulate species like iodine and cesium, they may not leak out as much, so we would assume a 1% for cesium or 10% for iodine emission from the reactor inventories. I also have there highlighted our half-lives for each of these radioisotopes, and in particular, I'd like to point out some of the ones with the shorter half-lives, like our xenon 135 and our iodine 133 and 135. So these are the radioactive decay chains for those species that we included in our simulation. And I'd also like to point out that it's difficult to discriminate between the xenon-133M and 133 because of the close proximity and the gamma spectrum of those two. And so being able to discriminate that actually is very helpful for us. But like I said, those short half-lives, what they do is they increase our sources from just the inventories of the xenons. We have these iodine isotopes that are decaying into the xenons, either indirectly through a metastable state or directly into the xenon. So I'm going to be talking mostly about the two chains there on the left, the iodine 131 and the iodine 133 chains. So for those chains, we can break them down very easily into a two-step decay chain process, and this can be modeled with a simple set of differential equations that are linear and without branching ratios, but that's a minor detail. And you can solve these by analytically integrating these depletion equations, and once you've done that, you can use the atmospheric transport model concentrations and then scale as a post-processing step based on these depletion calculations and based on a source intensity estimate. That way you decouple your atmospheric transport model from your radiological decay, and you can do that as a post-processing step to save computational complexity. So this is some graphical depictions of our Fukushima simulation plume concentrations. This is in particular xenon-131M, and you can see in the top left that it starts out in Japan and just kind of goes eastward towards the Pacific Ocean and then travels eventually all the way across to the United States and mostly stays in the upper northern hemisphere and just spreads out from there. So our closest detector that we have access to publicly, the US station, is Wake Island, and this is our simulation results compared to the measurements that were obtained at that station during this time. So the black line and black points are our flex part simulation, and the green and blue are the actual data. Now, on the bottom, I have also plotted the actual observation data versus the predicted based on our model, and the dashed line there is the 1:1 ratio, the y equals x line, so you can kind of get an idea of how well we're doing with our comparison. And this is, I would say, fairly good, given all of the uncertainties in our simulation with the meteorological data, source intensity estimates, because the magnitudes can vary very greatly. And so our second closest station is here in Oahu, Hawaii, and we again pick up some pretty good comparisons to our data. You'll note on the xenon-133 and 131M concentrations, you get this very strong dip in the concentration picked up, and we see that both in our data and our simulation, so that's a good indication that our atmospheric transport was doing pretty well there. Then finally we have Ashland, Kansas, and this again is doing fairly well, and that's a pretty long distance for the particles to traverse the entire Pacific Ocean and get to Kansas, so we're still doing pretty well there. Then we also looked at some particulate data, and in particular looked at cesium-137, which is what we also get from our IMS station data. Now, the long half-life of cesium allows us to focus mostly on the atmospheric transport capabilities of the codes and not on our radioactive decay. And you can see here in the black we're over-predicting what the magnitude of the concentration is, and this is assuming a 1% release from our reactor inventories, which is fairly small. So to me, this is indicating that our atmospheric model is not accounting for the deposition correctly. Indeed, it is actually turned off in this simulation, and the reason being because if we turn it on, actually, we see no data. And this is at a station in Wake Island, actually, as well. So this indicates to me that our FlexPart simulation has some real problems with the deposition model and definitely needs some improvement. But you can see that temporarily that we're getting kind of the rough temporal behavior. We have a lead on the first peak there, you can kind of see, and then the next two biggest peaks, you can kind of see that those are in the data as well, but they're sort of stretched out. So to me, this indicates that we're not getting the atmospheric transport or maybe the release time dependence correct exactly. So if we spread out the release a little bit more in time, it'll probably look a little bit better. Okay, so some of the key key results that we've gotten from our Fukushima simulation are that the simulations from the Takasaki station, our closest station that we have access to the data but can't talk about publicly, are underpredicted. So that's a little bit concerning, and probably has to do with the locality of the atmospheric transport there. We, as I said, have been focusing on xenon 131M and 133, and this is fairly typical in the literature, mainly based on the half-lives. They're some of the longest half-life species, so they're fairly easy to pick up. But we also have an issue with xenon 135 that we did not simulate some of the background sources of xenon 135, and as I said, it's one of the shortest half-lives, so it decays out pretty quickly, and that indicates that, to me, there's a lot of background sources that we haven't been accounting for yet, and so our results don't quite agree with our data there, and so we need to figure out how to incorporate background sources of xenon 135. The discrimination, as I said, between xenon 133 and 133M is still a challenge for us because we can't really use our xenon 133M data because essentially the background subtraction calculations on the concentrations from our detectors yield a negative concentration. So we need to be able to discriminate better between them, and so in order to be able to use all three species. And the use of more than two species, and in particular 3 and 4, all of the radioxenons, 135, 133, 133M, and 131M, they are used for discriminating civilian and clandestine activities, including weapons testing. So it's important for us to be able to get all of those signatures in order to do that discrimination. Only having two, it's very difficult for us to be able to discriminate them. Then with our FlexPart model, as I said, we're currently over-predicting our concentrations, but I do believe that's with the deposition model being a deficient model currently. And so the second set of data that we looked at was a volcanic eruption set of data, and we wanted to compare, again, our simulation to this data and compare our simulation to some of the previous literature values on this, using different atmospheric transport codes. I mentioned FlexPart already, but another one that's commonly used in the United States is called HiSplit, and we want to look at the capabilities of these two codes in comparison. The meteorological data set, again, is the CFSR data set. So the setup of this simulation is a volcano in Iceland, and we have a vertical line source on this volcano's latitude, longitude, and this line source varies temporally. So you can see on the y-axis the intensity of the height profile, and then on the x-axis the temporal profile of the emission. And so we coded this into our simulation, and we also had to discretize the mass emission by particle diameter sizes so that we have actually 54 different species being transported, and that accounts for all of the mass being released in each of these particle bins. So one of the things we did was compare to some of the literature values, as I said, and we tried both with and without deposition model. On the left, you can see that we have, with the deposition model, a severe underestimate of the data. Again, that's because with the deposition, the particles just fall out of the atmosphere very quickly. And on the right, you can see we're doing a little bit better. And in fact, we sometimes are overestimating the literature values. And so without the deposition, we get much better agreement, and the particles stay in the atmosphere a lot longer. Generally, they're within about 10% in the inner parts of the plume, but on the trajectory, the outer perimeters, you can see errors of 100% or more. So we still have some work to do there. And finally, some of the aircraft data that we have for comparing concentrations. Essentially what they did was they flew an aircraft with some sensors that can pick up particulates and count them, and they are able to get from that a concentration of these different particles, and we can compare along the trajectory to our entire atmospheric transport model, which has global data, and interpolate, and then we can do a comparison. Now, you can see here that the observed axis on the x indicates that we're again overestimating, or underestimating, sorry. No, the observed is higher. Yeah, well, I mean, the underestimate at the beginning of the simulation, actually, because you can see there's some real groupings of data points there. The start of the trajectory of the aircraft, it had a large reading at the beginning and the end of the trajectory. So it's possible that they were actually picking up not ash species, but actually picking up sulfur dioxide. And this is one of the concerns that we have with the instrumentation on the particular plane, and we need to be able to account for that discrepancy there. And so finally, some of the improvements to help discriminate between the Xenon 133M and 133 would definitely be useful to our capabilities, and incorporating some of the radio Xenon 35 background in particular would be helpful for our comparisons to data in the future. The dry and wet deposition models in FlexPart will probably require some improvement in order to be useful to us in the future. And we would like to compare different meteorological data sets. As I said, we were using one data set from the NCAR and in the US, and there's another data set in Europe called the ECMWF, which has a larger kind of amount of data, but we generally don't have public access to it because only the European member states have access to that. So we'd like to be able to get some subset of that data and look at that. And finally, the IMS stations, as Dr. Garces said, we're so far not able to pick up any meaningful detections from the DPRK weapons tests, but we're still looking at that data, trying to see if we can figure out what's going on there exactly. And in the future, we'd eventually like to be able to use some adjoint source reconstruction techniques with Kalman filtering and Bayesian maximum a posteriori estimation, and that'll incorporate the backward transport models that these codes are capable of, and eventually be able to estimate an optimal source set of parameters in either a parametric or non-parametric sense, including the uncertainties on those. And that's all I have.
This is so-called C wave, which basically is rather like the way that optical light is trapped inside a fiber, a low velocity channel. And